Hi, my name is Tianyi Zhou, and today I will give you a presentation about our paper Deja Vu, Contextual Sparsity for Efficient Large Language Models at Inference Time. And in this paper, we showed the existence of contextual sparsity in attention heads and the MLPs. And so by leveraging the contextual sparsity, we propose the Deja Vu, a system that uses a low-cost algorithm to predict contextual sparsity on the fly given inputs to each layer. And large language models such as GPT-3, PaLM, and OPT have demonstrated that a large number of parameters unleash impressive performance and emergent in-context learning ability. They can perform a task by conditioning on input-output examples without updating their parameters. However, they are super expensive at inference time. Retraining or iteratively pruning large language models, which have hundreds billion of parameters, is currently infeasible. Techniques that are effective for smaller models, such as iterative pruning and the lottery ticket hypothesis, are not suitable for large language models. This is primarily due to the massive scale of these models. Another significant challenge lies in preserving the in-context learning ability of LLMs, and the task is to find a level of sparsity that does not compromise this ability. While pruning dependent on specific tasks has proven to be effective, it poses a contradiction to the fundamental goal of task independence in large language models. Contextual sparsity refers to a concept involving small input-dependent sets of attention heads and MLP parameters. These elements are significant because they can produce results that are approximately the same as those of the full model for a given input. The existence of this type of sparsity is particularly interesting. It suggests that we could potentially deactivate specific attention heads and MLP parameters without significantly impacting the output. And this approach could lead to more efficient models as it allows for the trimming down of unnecessary components while maintaining the same performance. On average, we can apply up to an 80% of sparsity level on attention heads and as much as 95% sparsity on MLP neurons. It's interesting to note that the OPT 175 billion model processes double the number of MLP parameters compared to those in attention blocks. Therefore, the total sparsity in this context approximates around 85%. It is important to understand that these sparsity levels are all structured, focusing on heads and neurons. Consequently, if we predict these elements accurately, it could potentially lead to a 7 times speed up in input processing. So as we can see here, figure 3b reveals that we can achieve up to like 95% contextual sparsity in a token within the MLP block. Identifying this sparsity happens post-activation computation. However, merely identifying it doesn't improve the efficiency. To use this sparsity effectively for better end-to-end efficiency, we need a method that is both rapid and accurate. So this is crucial for making the most of the contextual sparsity. Similarly, in attention blocks, selecting attention heads quickly and without full computation is the key to reducing latency. And a unique challenge here is the dependency of the attention on preceding tokens, adding complexity to sparse prediction. So in our research, we have found a high cosine similarity between embeddings or activations in consecutive layers of different size OPT models. This insight led us to use a neural network classifier for near neighbor search. And for each MLP block, we train a small 2-layer network to predict contextual sparsity. The training data is easily obtained from dense computation. Similarly, we predict sparsity for attention heads. Considering their dependence on previous token, our attention sparse predictor uses the same architecture as the MLP predictor. Each head is treated as a separate class, following a similar training process. The predictor select a set of heads as explained in our algorithm here. Um, and we also address the issue of missing KV cache for past tokens. We compute and store keys and values for the predicted attention heads of input Y in the KV cache and keep a copy of Y for all other non-selected heads. In conclusion, we present a significant advancement in optimizing large language models like OPT 175 billion, and this study uncovers the concept of contextual sparsity, capable of achieving up to 85% sparsity in attention heads and MLP parameters, maintaining output quality. And the proposed Deja system effectively predicts sparsity in real time, considerably reducing inference latency with some hardware-aware design. And this development not only boosts processing speed, but also sets for some future AI research, offering a blueprint for scalable and efficient AI system, adaptable across various scales and applications.